So if you look on this section, so up here at the top, you have, yesterday we talked about the one down below, B equals mu naught I 2 pi r. That gives you the strength of a magnetic field in relation to a wire. Today's lesson is going to be QVB sine theta. So, you got to stay with me through this transition. So, if you start with the equation itself, this is a value of force. That's what the F stands for. And instead of saying, oh, it's Fg created by a gravitational field, this is going to be Fb created by a magnetic field. Now, what? Huh?
Why is it Facebook?
What do you mean? Why is it?
Because magnetic
Force
field.
points, yeah.
Because a magnetic field,
What is this?
just like yesterday, B equals mu naught I over 2 pi r.
Why the B though?
B,
Bro.
Because magnetic field.
B is for
B
boy, Elliot.
shows a magnetic field.
Yeah, but why not
Why
the
do
B?
they pick?
Yo, why was
Not
force
like
labeled with
and.
F?
Bro,
He's
why
not
that letter
eyes
though?
and
I think that's
stuff.
okay.
So SB is magnetic.
Because they can't use N because N is mass.
Then use capital M.
B.
Are you saying it
What are
physically?
you?
Don't ignore it.
Just
Are you saying
ignore
it
it, bro.
physically
Just
shows
don't
a
worry about
magnetic
it.
field by the line?
Huh?
Are you saying it physically shows a magnetic field
Bro.
by the line?
Oh, I like
Okay.
Wait.
So, FB, force through a magnetic field. There's 3 criteria. Number 1, you have to have a charged particle. Neutrons don't do this. It has to be a proton, electron, an ion, sodium that's lost, charge, something like that. Okay? V is velocity, that is not voltage.
Or volume.
Okay? Or volume. So that's velocity. Okay? B is the strength of the magnetic field. Okay? And the sine theta part indicates like what's going to happen with the angle relative to the magnetic field in that motion. So, magnetic field strength, force, 3 criteria. Basically, you have to have a moving charge going through a magnetic field. Okay? So, this is why if you look at like what creates the northern lights, which have actually now been visible some even recently in Kansas.
Uh-oh.
So, here's the Earth. You have a magnetic field. You have charged particles coming in from the sun. Those charged particles have a velocity. They come in and they interact with the Earth's magnetic field. That creates a force on them, and they change their direction and they get directed towards the poles. This is why you have northern and southern lights, because that's where the field strength is the most intense. So, the value of the calculation is just QVB. Now, here's the deal in terms of the units. So the Q has to be in coulombs, obviously. Okay? So that has to be in some coulombs. You have to have a velocity in meters per second. The magnetic field strength is going to be in Teslas. Okay? Now, this is where this gets a little bit weird in terms of Teslas. If you break Teslas down to its core fundamental units, that's Newton seconds, coulombs to the -1, meters to the -1.
Whoa.
Hold on.
Newton seconds.
Okay? Now, this is why this, so these are the technical units of Tesla. And this is why this works. So you have a charge which is in coulombs. That cancels out the coulombs. It does.
I just don't like it.
I don't care. So then you, I'm just telling you. So don't kill the messenger. I'm just telling you.
Oh,
Okay? So this whole thing is taking the place of Tesla. So then the seconds cancel out, the meters cancel out. The only thing you have left is
forces in
newtons. Okay, and that's what the force is measured. So Teslas are technically coulombs, meters to the -1, Newton seconds.
Why did you say that?
I don't care. Okay? It's just like, again, fight the tides. Good luck with it. Okay? But it makes the units work out. Now, here's where this is going to play out. We're going to use the right-hand rule, a different version of it. Now, listen to me very carefully. This is based upon positive particles. Okay? Not the current. Current's a different thing. These are positively charged particles that are interacting with the magnetic field. Okay? These are positively charged particles. Now, so let me give you an example of how this works. You have to involve three things: your thumb, your index finger, and the fingers itself. Okay, so this is like this physics little gang sign. Okay? So, the thumb shows you the direction of the current.
Alright, that's the same, Bo.
Okay? That part's the same.
I did it to myself.
Okay, it looked like you were
Your index
No,
finger,
I did it to me.
your index finger is the magnetic field. Okay?
Oh.
And your fingers, the rest of them, show the direction of the force. Okay?
Wow.
So this is why it looks like you're shooting a gun. Okay?
Oh wait, we closed these three?
Yes.
So it's
Close
like
these.
it's like that's it's actually a gun. It's
Now-
literally a gun.
Here's where the sine theta part comes into play. What's the sine of 0 degrees?
Zero.
0. So what that
What
means
are the fingers?
is if this proton
Yeah.
is moving in the same direction as the magnetic field,
Oh, zero.
they're not going to experience any force. But if the charged particle is moving at a right angle to it,
Sine of 90.
sine of 90 is
One.
1. So your maximum force is going to be occurring where?
Perpendicular.
Perpendicular to it. Okay? So your maximum force is going to be when a charged particle is moving at right angles to a magnetic field. So this is why if you look at the Earth and its magnetic field, right? So you get these charged particles that are coming in from the sun. So they're going to have a magnetic, so they're going to be interacting with the Earth's magnetic field. So here's a simple example. So our Earth has a magnetic field, okay? Which direction is the
North-south.
magnetic field?
NTS.
North to south, right? Okay? So the magnetic field lines of the Earth is actually coming around like this. So let's say that you have a charged particle from the sun, okay? And it's going in a particular direction, perpendicular to it, right? So then you can figure out, oh, okay, what's going to happen to that force based upon the motion of that relative to that magnetic field line. Okay, so let me give you a simple example. We're going to start with a simple example. All right? Best to start with that. So, we're going to have a wire. We're going to start with a wire. And the current in the wire is going to your right. Okay? So the first, you got to use the right hand rule twice. Okay? So stay with me here.
Stay with me now.
So, and we're defining the current like Ben Franklin current. Okay? Ben Franklin current. So the current's going in this direction. So what's the direction of the magnetic field around that wire? On top, what are you going to have? Dots or X's on top?
What? Yes. X is on the bottom.
Oh, it's my left hand. Control and hang on.
So right hand rule, going like this.
Why is it always
Yeah, he's my
right?
left hand.
Good?
Yeah.
So up on top, you're going to have,
Dots.
bottom, you're going to have
X's.
X.
coming in.
Okay. So I got dots on top. I've got X's
That's it, that's the second one.
on the bottom.
Does it matter how many X's are
No.
dots?
It does. You're just showing what's happening.
What?
Okay? Now, here's the deal. I'm going to shoot a proton. Listen to me very carefully.
Positively charged particle.
I'm going to shoot a proton
That's so
in this direction.
Zero.
Okay? So this is a proton. It's going to be going parallel with the wire.
Oh, that's not.
Okay? It's going to be going parallel with the wire.
Signs it.
But it's going to be at right angles to
The
the
electric
magnetic field. So we don't have to worry about the sine theta part of it. So, you do this. You take your thumb and you point that in the direction that the positively charged particle is moving. So I got this action. Okay? So that's going to be going like this. Now, that's going to be going like this. But what do you have up on top? Dots or X's? So what does that mean?
Coming out.
Coming out. So I'm going to go like this, and then I'm going to take my index finger, okay, and I'm going to point my index finger out to the page. Okay? So which direction do my fingers point?
Out of the
Down.
No, they don't point out of the page.
Down.
Excuse me,
Down.
which direction
Oh.
do these four
Oh.
fingers point?
Down.
Downward.
Downward.
So
Bro, my
I
fingers
got
are that
the proton going like this.
My fingers hurt.
Proton's going like this.
Yeah.
The magnetic field is coming out of the page. Right?
Yeah.
Yeah.
My fingers point
Down.
down. So, what's the proton going to feel? An attractive force towards the wire or a repulsive force?
Attractive.
It's going to feel an attractive force.
Right.
So the proton is going to feel an attractive force going down like this.
Wait,
Right?
Because
But so if it was traveling
These are down.
under the wire on this side, would it go?
Hold on,
Like
just-
three
just
other-
chill out. We'll get there.
stupid finger.
It's going down.
Okay, so magnetic field.
I don't know that.
So,
answer.
everybody cool with this? We use the right hand rule twice. The first time, we just had the current. We use the right hand rule to figure out what's happening in terms of the magnetic field. We use the right hand rule, the current's going this way. My fingers are pointing out, that's why that's dots. This is why I have X's down below. Good with that? Cool. Now, once we establish that, then we use the right hand rule a second time. Okay? So, I have to use my index finger, my thumb, and my balance of my fingers. So I've got the proton is going in this direction. Go with this. The magnetic field is coming out of the page. So I got this action going.
Toward my face.
Well, we're out,
Yeah.
okay?
Just say,
And which direction are these fingers pointing?
Straight down.
Straight down. So that's why this is going to feel an attractive force towards the wire. Okay? Okay. Opie.
Okay, this is super cool. Like, I don't understand. Why is it that like it faces out? Is it always like out of the page? Like, how come it's not up? Does that make sense?
This is the magnetic field that's circulating. Let me try and draw this without making it worse. So this is the magnetic field that's existing in circles around the wire. That's what that charged particle is interacting with. Okay? So as that proton goes through, imagine here's the wire and my fingers are the magnetic field. So as that proton goes through, it's going to interact with this magnetic field around the wire. So here's the stopper. Okay? This is my proton. It's going to come in. It's going to hit that magnetic field around the wire. Not the wire, the magnetic field around the wire. And then it's going to feel an attractive force, and you're going to see that thing begin to drift downward towards the wire. Does That makes sense.
Yeah, but I was saying like whenever you kind of like
So it's gonna be trial.
how come it's not like
We
like
went
whenever
not
you're
here.
doing this, how come you like turn it your finger?
Oh, it is.
Okay. The reason that I point it out, because
Looks like a particle
up
accelerator.
here, those circles, the direction of that magnetic field is pointing out of the page. That's why I pointed my index finger out of the page.
Is it always like?
No, avoid the word always. Stop.
Yeah.
Using the word always.
Okay.
What is always going to be true is that your index finger just always points in the direction of the magnetic field. That's the only thing that's always true.
You said, wait, you just said never says always.
In terms of like, I know her thought process.
Oh.
I don't know.
Oh, dang.
Always the next
Oh,
okay? You can use the word always, but not how you were trying to use
It's only a
it.
windstorm.
Okay? Now, what if we take the same proton,
It's gonna be at an angle, huh?
and we're gonna put it
but we
underneath it.
shoot it
Turn the AC on.
on the bottom side of the wire?
It go up.
Okay,
down.
just
Look.
Okay. So, the positive charge is going this direction. Okay? You have X's, which means what?
We're going in.
The magnetic field is going into the page.
Yeah.
So I put my thumb in this direction. My fingers, this index finger points into the page. Right? Which direction do these fingers point? Up. Upward. So even if the proton is on the bottom side of the wire, what's it going to do?
Go into the.
It's going to feel an attractive force
We're
upward.
all gonna look so retarded.
Oh, I love watching it.
Oh my God.
It is the funnest test to physically watch kids take.
You'll probably like crash out watching me do
So
it.
we'll go to the top. Or no, we'll stay on the bottom. So when I do my thumb, and then I do my index finger, this 90 degrees right here,
Yes.
Well,
always.
Wait, when is it?
That's a
not
good
nice?
one.
Only if you have to be told something different, like 45.
Oh, look, you get told the angle.
No.
Yeah.
Wait, what?
Now,
Wait, you get told the angle.
what if we have the same wire with the same current, still the right-hand rule, on top we're still going to have circles, on the bottom we're still going to have dots.
Okay.
But now I'm going to shoot a proton
Oh.
in the opposite direction.
what is
Okay.
that?
So, proton's going this way.
Swing, man. Right.
This is where you have to be a little bit gymnastic.
Hey, my fingers can't really do that, Mr. Bird.
Sorry. So, you're going to go this way. On the top, which direction does the magnetic field point?
Oh, Lord.
So you got to lay your hand over like this.
Yo!
Okay?
Yo,
This is like, this is
is that a
yoga.
proton?
So I'm going to lay my hand out like this. Which direction do my fingers point?
Hold on.
Upward. So a proton going this direction is going to feel what?
Repulsion.
Yes. It's going to feel repulsed. Okay?
Stop making us feel inside.
Imagine if this here, bro.
Wait.
Hey, alright, that's it.
Now,
Take this over there for now. That's it.
I'm like so dumb. We know the test like.
if I take that positive charge and I'm on the bottom side, okay? Don't confuse an X with a cross, okay?
Wait,
Not.
current goes.
So now, the proton's going this way. I'm on the bottom side of the wire.
Well, it's repulsing again.
It's going this way.
No. Why are you making up your
The X's are going into the page,
Because if you
okay? Which direction do my fingers point?
Down.
I guess that.
Downward. So,
if you could
therefore, even on the bottom side,
You're pointing this way.
it's going to feel a repulsive
wait, how do you?
force. Okay? All right.
Just keep going. It's fine.
Right.
I already broke my wrist last week.
Shannon.
Can I not do that?
This
Oh,
your
I broke
hood?
my wrist. Oh, I'm so
Hey, for the test, just bring a prosthetic hand, Michael.
Wait, that might be
Josh,
a method.
hey. Josh, what?
When you're doing it with your hand, are your like other fingers supposed to like be straight and they stay straight, or do you like curl them?
No, those, it's always at 90 degrees. Okay, so this makes a 90-degree angle between your index finger and the thumb.
That might be the method.
This makes a 90-degree angle between the palm and these fingers. The only time it's not at 90 degrees is if this represents the angle between the path of the velocity and the magnetic field. Now, contemplate this. What if the particle is moving parallel with the magnetic field?
Oh, then nothing happens.
Then nothing's going to happen because it's moving parallel with it.
Sign 0.
There you go.
Yeah.
Right? Good with that. Good with that. Now, we'll change that.
What kind of thing was that?
Same wire, same current, going in this direction. We're still going to have dots on top. We're still going to have X's on the bottom. Go with this. Now,
Keep doing this.
Oh, the particle's gonna go straight.
I want to shoot an electron.
You said it was.
The left hand rule.
It's a different.
Now, there's two ways that you can do this. This is a personal preference. Now I'm going to shoot an electron. Okay? I'm going to show you both two ways you can do this. How you do this, I don't care. Okay? One option is that you treat it like a proton. Okay? Same thing.
Like where your head's at.
Proton going this way, the magnetic field is coming out. The proton, if it were a proton, would feel an attractive force. If it was a proton.
What's an electron? So it goes up.
But since it's an electron, you do the exact opposite,
I like that idea.
and it would feel a repulsive
We
force.
already did it.
Okay.
Like your head's at, like your head's at.
So, that's an option.
That is the
You
option.
can- I'm just telling you, it's an option.
Wait, what's the other option though?
But for additional shipping and handling, there's another option. You can use the left hand rule.
Wait,
Oh! Some people like this. So it's the same idea. But I use my left hand. I put my thumb in the direction of the electrons. What's happening with the magnetic field? What's it doing?
Coming out. And that
Coming out. So which direction does my fingers point? Upward.
I can't do this with my
And it's
hand.
gonna go up. So, if it's an electron, you have one of two options. You either treat it as a proton, figure out what's gonna happen, and then you flip the direction.
It was.
Or you use the left hand rule. Okay?
Can we run it back?
Whichever one
Hey,
they
can we run it back?
What?
There'll be lending problems on this test.
Oh, no.
Why would you even ask that?
Bro, because like, I don't know.
Short question
yeah.
the test.
It will be, but it'll be magnetic fields and electric fields.
No!
It's gonna be cool.
Why are you happy
Adam,
about
I think I got
this?
lost.
Because now,
Can we run back the left hand?
So it's like,
let's talk about this.
because it's like,
Yeah, long
because it's coming out.
So it's being. This is current.
It's the same thing. Like each
So the
finger
right
is
hand
the
rule is
same
always
thing.
like this.
Is this
He's
current or
changing
is
which
this
orientation
direction?
you're
of
going.
the-
Point a gun, alright?
Direction.
You go like this.
Yeah.
Oh. And then you just move to which way.
So I'm doing X's and circles and.
Yeah, it's either going in.
So it's just gonna be
like
repelled like that.
Or out of the picture.
I'm an archaeologist.
Not even
Yeah.
second.
I didn't even draw.
Now, here's an interesting idea.
I don't like that idea.
Oh, they field, boo.
You have a particle moving in a circle
Oh.
in a magnetic field.
Oh.
Is the particle a positive or negatively charged particle?
Wait, repeat.
Okay, so
Huh?
you have a particle moving in a circle. Okay? This is where old school meets new school.
Gavin.
You have a particle moving in a circle like this. Cool? The particle is moving around like this.
What are all the
Like
X's?
counterclockwise?
What do the X's represent? It's a valid question. That's your external magnetic field. So what's the direction of the external magnetic field? In or out? In. So the particle is going like this, right?
Oh.
Yes.
What's the direction of the magnetic field? In or out?
In.
In.
So it's going down.
So which direction do your fingers point?
Down.
What I mean,
So is it a proton or
Is it a proton or an electron?
what do you?
Wait, listen,
Like right hand.
We're going this way.
Hey, Burkamp, can we run that back?
Can you repeat
Run it back.
It's like not processing.
Wait a minute.
Okay.
because it's in.
So there's a circle.
Yeah,
This particle is going around like this
counterclockwise.
in a perfect circle, right? The magnetic field is going into the page because you have X's. So I'm going to take my thumb and I'm going to point it this way, okay? Because that's that instant, that's the direction that it's going. Go with this.
Yeah.
Now, the magnetic field is X's. So which direction is my index finger going to point? Inward. So I've got this action. Which direction do these fingers point?
It's a positive.
These point inward. Now, what's the direction of any centripetal force?
Out.
Center of the circle.
Oh wait.
It's a positive, I promise.
What do you say?
I promise it's a
Yeah,
positive.
More than a 90 degree angle.
It's
That's gotta be
going.
lashing.
To the center of the circle.
This is. It's going into.
It's a positive.
Which there's already an X in this.
The direction of any centripetal force is inward at a right angle to the
Velocity vector.
velocity vector. So, if this was a positively charged particle, which it is,
Oh, what did I say?
so thumb's going like this, the magnetic field is this, the centripetal force is acting inward. Would I get the same result if the proton were over here?
Yes.
Yeah.
Why?
It's always the same.
It always goes in.
Because even if it's here, my thumb is gonna point down,
Yeah. Got it. I got
my
it.
index finger is gonna point into the TV, these fingers point this way.
Don't worry about it.
Is there
Now.
a way to do this? I don't know.
What if
No.
Wait. How does that make it a proton?
Oh my god.
Oh,
Wait,
you're
so
still
turn
just
it-
right next to it.
Because
Look, it goes down. Force goes
So
down.
when the force goes in, it's a proton.
It's going in
the
counterclockwise.
centripetal force always acts inward.
Yeah.
But this fits with the right hand rule, and I'll show you why. If the particle
Right hand rule and it agrees with it.
was going in the opposite direction,
Okay.
Okay, you gotta use this.
okay?
Oh.
Here's the thing. If the particle was going in the opposite direction like this,
Oh, that doesn't work.
okay?
They go
The
out.
magnetic field would be pointing inward, but the force, if this was going in this direction, my thumb would be pointing like this, my index finger would be going like this,
Force go
and the
out.
force would be pushing outward. Is there any force that pushes it outward to make it move in a circle?
Centrifugal.
No.
Oh.
That's naughty boy. Hit him, bro.
So a proton could not go in that direction. But what could go in that direction?
An electron.
An electron.
I'm understanding.
So if you use the left-hand rule,
No. I mean, yeah.
popcorn, show out. No, go, this is So, if
I don't like
use
these
the
conceptual
left-hand
questions,
rule,
bro. Right.
Left hand's for
I put my
Yeah.
thumb in this direction. My index finger is still going to point inward. My fingers
My teacher's gonna think I'm
point
crazy.
that
I
direction.
know, we're just like sitting here.
That would be an electron. So this is how you can figure out the charges on a particle.
So if it goes.
Put them in a magnetic field. See which direction they move in a circle. So if you know that they're moving, like in this situation, if they're moving in a counterclockwise direction,
Positive, you know.
they have to be a positive charge. If they're moving in the other direction, they have to be a
Negative.
negative
I
charge.
have a question, Mr. Burkett.
Hold on,
Is that always?
always.
Oh.
Listen,
Are we
I thought you said
looking
no always.
straight on?
huh?
Are we looking straight on at a wire, or are we looking at a loop?
Oh, no, there is no wire. Oh, no. There's no wire, there's no loop, nothing.
Electric field.
Okay? There's not even an electric field.
Wait,
All this is the path of the particle. This isn't a wire.
Electric
All
field,
I'm
right?
showing is that this is the path of the particle.
Oh.
Okay? So, imagine this. I've got a magnet out here creating a magnetic field that's going into the page. And I look and I see a particle moving in that circle.
How do we know which way your thumb goes?
Huh?
How do you know which way your thumb goes?
Because your thumb always goes in the direction of the velocity.
I thought thumb is right.
Huh?
Wait,
I
it
thought
says
thumb
also
That's if it's a
particle
wire.
because
This is
why?
a moving particle.
Because if
That's
you're
why
using your
there's
right
two
hand to give
versions
an
of the right
inverted force.
Dude, I might get.
Because if it's
So
moving
wait,
in a
it's the
circle, the force
direction
is
of the
always
particle
inverted.
velocity?
So
Yes.
if it's left hand, it's a left hand.
Okay.
The thumb is
If
your
it
velocity.
was an electron, you go in the opposite way.
Oh.
Your
But you still need
fingers are
to, you
the
can't,
direction of the force. Your index finger is the direction of the magnetic
because then
field.
it's out. Then it's outward.
So thumb
So
is
that
velocity,
doesn't work.
index finger is magnetic
So you
field,
have to,
fingers
it's
are
an
force.
electron.
Are there test
It is
retakes?
a wire.
No.
Mr.
Read
Burkett.
corrections.
Corrections definite.
Oh,
How much percent?
like,
I don't know.
100%. Like 50
What?
or
What if that was an O, not an X?
Now,
Oh.
oh no, that's a valid question.
Wouldn't it be the opposite?
As opposed to all my X's living in Texas, all my O's live in Arkansas.
Why'd you have to open it?
Huh?
What does that even?
So, there's a song by George Strait, all my X's live in Texas.
Oh, I know that one.
I know, but where'd you get it?
Oh, I hate the song. I
What?
love George Strait, but I hate
Is
the
it true,
song.
Mr. Burkett?
So,
So,
I have a particle
ask me like.
moving in a magnetic field that's going in this direction.
Yeah.
Is it a positive charge or a negative charge?
Negative.
Why does it have to be negative?
It's left hand rule.
Left hand rule.
So, start with this idea. If this thing's going to move in a circle, which direction does the force have to act to make it move in a circle?
Middle.
Towards the center. So I know no matter what, my fingers have to point towards the center. Okay, I know that. So, let's say I'm saying the right hand rule. I'm going to start with that.
It all makes
So I've got
sense.
my right hand going like this.
You bend it back.
But
Up.
what's the direction of the magnetic field?
Out.
out.
So what am I? So I got to lay it over like this. Ah!
Oh, but our force is up. That makes no sense.
That makes no sense because if I use the right hand rule and the magnetic field is coming out of the page, my fingers point upward. And it would force it out and not go in a circle. But if I use my left hand, it's going this way. The force is coming, bang, out of the page, and then these
Yeah.
fingers point inward.
What the crap? What the actual crap?
Can we bring up
I'm assuming it gets worse.
Which means this is going to be an electron.
Can we
So
quit
there's two
now?
ways you can think about it.
This is it.
Okay? There's two ways you can think about it.
Stay too.
I don't care how you do it. If you always want to use the right hand rule, always use the right hand rule.
Actually, I'm using two hands.
It's going like that. It's coming out. Then if that's the case, the force would be pushing it out. So it can't be a proton. Then it has to be,
Electron.
It's like- okay? Or you can use the left hand rule. Now here's where the math kicks in.
We're not even doing.
Let's just keep it with two.
No. If you're moving in a circle,
Two more.
hold on.
Wait, is that not a circle?
If you're moving in a circle, there has to be some centripetal force.
Oh dear. Oh dear.
What's going to create the magnet? What's going to create the centripetal force?
Magnets.
The force of the magnet. Now, if it was a planet, what was creating the centripetal force? Gravity. If it's this, what's creating the centripetal force?
Tension.
String.
Uh-oh.